Hi everybody. In lesson 2-6, we're going to build on what we talked about in 2-5 about light bending and absorbing and reflecting to talk about how we see colors. So let's jump right in. Alright, so color. It's important, like when we use the diffraction glasses, it's important to realize that white light is not a color. It is made up of a mixture of the 7 colors of the rainbow. There are more colors obviously than that, but we're talking about the major colors. So remember again from our lesson 2-5 that in a prism, which looks like a triangle, light is always going to bend towards the base. So white light is going to come in, and because each one has its own distinct wavelength, it's going to bend through the prism at a slightly different angle, and therefore all of the light is going to spread out and you're going to be able to see every single wavelength. Now, here are the colors of the rainbow. Roy G. Biv. Red, orange, yellow, green, blue, indigo, and violet. Now, as you can see here, I hope you can see that. You got to look really closely to see the violet. You can see the dark red. What you're looking at are the relative wavelengths for each frequency of light. So remember, in sound, frequency represented the pitch or tone of the sound. In light, frequency represents the color. So hopefully you can see that violet has the smallest wavelength and the highest frequency, whereas dark red has the lowest frequency and the longest wavelength. So dark red has the lowest amount of energy than of all the visible light. If you're looking there at that scale, the NM stands for nanometer. And then you see that A looks like it has a little halo above it. Right? That is the metric unit angstrom, which is what we use to measure very, very, very small distances. The distances between 2 atoms in a molecule is often measured in angstroms. All right, so how do we make the different colors? Now, it is important to realize now that what we're talking about right now, when we're talking about color, is about light. We are talking about light here, not paint. When you talk about paint and pigment, you're talking about something different, right? And I'm going to show you the difference in class. So please keep that in mind. When we're talking about adding and separating colors, we are specifically talking about colors of light and not pigment. All right, so white light can be split up to separate colors, but colors can be added again to make other colors and then back to white. The primary colors of light are red, blue, and green. Not yellow. Yellow, that's a pigment thing. And that is what the lights look like. That is how lights mix. So hopefully this kind of looks like a Venn diagram, and you see that green and blue produce cyan. Red and blue produce magenta. Red and green actually produce yellow, and if you put all the 3 together, you produce white again. Hopefully you guys see that. All right, so when we see color, the color that we see is a combination of 2 things. It's a combination of light absorbing and reflecting and how our eyes perceive the color. So the color of an object depends on the colors of light it reflects. So for example, all right, this book appears red. It appears red because when I shine white light on it, all the colors of the rainbow come into the book. But the paint, the pigment that the book's cover is made of is shaped. The molecules that make up the paint of the book are shaped in such a way that they will trap all the wavelengths of light except for red. Red will reflect out like a little mirror and to our eye, and therefore we perceive red. So a pair of purple pants are only going to reflect purple light, or any combination of light that would make up purple. So again, all the colors of the rainbow would go in, purple would come out because the paint was made in such a way that it will trap the wavelengths of light that aren't purple, but so will red and blue. Red and blue will also come out because they make purple. A white hat reflects all 7 colors. So that means that all 7 go in and all 7 come out. They combine in your eye to form white. But that's only if we start with white light. If we start with a colored light, then only one colored light comes in and things can get weird. Alright, so here's a soccer uniform, right? We're just going to say. All the colors of the light, all the colors go in. The shirt is red, which means that means that only red is going to come out of the shirt and only blue is going to come out of the pants. So red light comes out of the shirt, blue light comes out of the pants. It reflects out. Alright, that makes sense. But if we hit the soccer uniform with only red light, obviously the shirt is still going to look red. But now the blue shorts, and this is pretty neat, the blue shorts can only reflect blue light. But I didn't add any blue light at the beginning. I only added red light. So that means the shorts are actually going to appear black because no light is coming out. Conversely, if I were to hit this soccer uniform with just blue light, obviously the shorts would look blue because the blue light would be reflected, but now the shirt would look black because no red light can be reflected from a red shirt if no red light was added to begin with. So we take advantage of this we actually take advantage of this idea when we use filters. So if I put a red filter, and we do this all the time in the Light Center when we try to make the stage appear or manipulate the stage to look a different way, to mess with the colors on the stage, we'll put little cellophane filters or acetate filters into the lights to block. Because remember, the big bright the big bright spotlights are pushing out all the different frequencies of light. If we put a filter above it, then we're actually trapping some of that light. So if we put a red filter, then that means only red is going to get through. Everything else is going to get blocked, and all we see is red. If we put a magenta filter on, only purple and the colors that make purple will get through. So, to sum up all the things that we've talked about so far about light. Light travels in straight lines unless it hits a new medium. Light travels much, much faster than sound, about a million times faster. We see things because they reflect light into our eyes. Don't worry about how yet. We're going to talk about that a little bit later. Colors are different wavelengths or frequencies of light. Shadows are formed when light is blocked by an object. And one that I didn't put on here that perhaps I should have is the difference between reflection, refraction, and diffraction, which you do need to know. So that wraps up everything that we've talked about as far as light goes. We have one more section left, and that is how our eyes and our ears work. But the main principles of light and sound are done. We are officially done with that part. So go ahead and do your homework, and you might want to use colored pencils for your homework this time. And I will see you in class. Bye-bye.